Now would like to switch to the last presenter of this free electron laser session, which would be Oleksii Liubchenko, and he is basically Ukrainian working in Poland and basically also user of European X12.
Thank you for introduction. Do you hear me?
Yes, but we don't see your screen for some reason.
Wait a second. And now?
It's coming, I hope. Yes, now we can see it.
Yes, and my talk is connected with ultrafast structure changes in iron studied by time-resolved X-ray diffraction. And in this work, we was using pump probe approach, which was very nicely present in last talk. We pumped we are pumping the sample by laser and some relaxation occurs and some structure transformation occurs, and using femtosecond probing method as XVLs, we can capture the structure changes in our investigated object. For now, it is a widely investigated subject as structure transformation in metals. It's searching of the question, how fast is the melting or structure transformation? And a good example is bismuth from last talk. And the next metals are investigated already, and our investigation is connected with investigation of ultra-fast structure changes in iron. There is a typical experiment schema. The experiment was performed on FXC instrument on European XFL, and the experiment scheme is shown on the slide. It is silicon frame with silicon nitride membrane with thin nanocrystalline iron layer with silicon oxide cup. And from as a result, we are obtaining 2D diffraction images for different delays after laser irradiation. And after integration, we are obtaining diffraction pattern. And what is interesting for iron and what wasn't observed earlier, it is appearing of additional break peak at lower Q position. Here it is shown integrated pattern and deconvolution using two pseudo-void function for break peaks and Gaussian function for the liquid hull. And we call these peaks in further as low Q and high Q according to their position in Q, and how looks like dynamics. Intensity decreases as is expected, some melting occurs and liquid hollow scattering occurs, and what is interesting that additional break peak appears after melting. And these obtained results were filtered, and from this we can obtain dependencies in time for peaks intensities, as shown on this figure, intensities of break peaks and liquid, and position of break peaks. Here are shown results for 13 microjoules energy. And looking to these plots, we can distinguish the following regions of structure transformation. First is the heating. It occurs in first picosecond. It's very fast, and actually we have no good resolution for this region, and it is characterized by decreasing of bragg peak intensity on 25%, and no liquid isn't observed. Next region is melting region. The liquid hollow peak occurs due to scattering from the molten iron, and at the same time intensity of the high Q bragg peak decreases. Also, we can observe some starting of lattice expansion as shift of bragg peak. And time region is up to 5 picoseconds. Next is the region of solid-solid phase transformation, where we observe appearing of additional bragg peak. Intensity of the high Q peak decreases, and intensity of low Q peak increases, but it should be noted that summit intensity of these peaks almost doesn't changes. And also some melting continues due to heat transfer into depth of the layer. And after that, we observe only slow changes, some relaxation region. And what we expect to see for iron? We are starting from alpha iron with body-centered cubic structure, and look into conventional phase diagram. We are moving through gamma iron region with phase-centered cubic structure to body-centered cubic delta iron, and we are near to the melting point for presented data. And what is the origin of low Q peak? It is not gamma iron, because if gamma iron will form, the summit intensity should change due to changing of unit cell and structure factor. And our explanation is that it is BCT distortion of initially BCC unit cell. Here the unit cell is schematically shown. Here are atoms, lattice planes, and before laser irradiation, we see only one interplanar spacing from the 110 reflection for iron from body-centered cubic cell. First approximately 5.5 picoseconds, we are observing 3D expansion of unit cell due to heating, and after near 6 picoseconds, the BCT distortion occurs. It is characterized by appearing of two different interplanar spacing, which gives splitting of peak, what we see from our experimental results. And what is the reason of such behavior? Theoretical calculation had shown that if we heat BCC iron over Curie temperature, some lattice instability occurs due to changing of magnetic order, because it is some changing of magnetic properties from ferromagnetic to paramagnetic. And this lattice instability gives that BCC lattice becomes more energy favorable, and it is so-called and well-known Bain phase transition path from BCC to FCC iron. And what if we assume that we have BCT distortion? We can from bragg peak position we can calculate lattice parameters and volume of unit cell, volume per atom. And here on this graph, we can see experimental results and values of volume for cold iron, for iron at Curie temperature and near melting point. And if we'll measure earlier, the low Q peak appears after melting, which means that average temperature of the layer is near to the melting point. So we cannot operate with Curie temperature, but our results indicate that that lattice expansion, that changing of lattice parameters over value of volume or lattice parameter of BCC unit cell over volume at Curie temperature, that induces distortion of BCC unit cell to BCT. So here our results indicate that ultrafast heating occurs at time scale near 1 picosecond, which indicates on strong electron phonon coupling in iron. We measured ultrafast melting, and we have first observation of BCT distortion from XRD data. Work was done with wide collaboration. Thank you, collaborator, for participation, and thank you for attention. Also, thank you for organizers for invitation.
Thank you very much for the talk. And now we moving. We basically finished the free electron laser session, and we as usually far behind of schedule. And now until 3:40 European time and 4:40 Ukrainian time, we have a short break and we'll continue with Daisy session research. But I'm very sorry, there was question from Mr. Dr. Professor Luc Patet. So please.
Okay, just thank you for this talk. I have a question. It seems to me in your time trace, you have not just low and high Q peaks, you have a third peak centered at 2.8. Can you comment on that?
Yes. Short peak,
it's a very at the beginning of your, yeah, go ahead. Yes, yes. Here at 2.8, it seems to be you have a peak here.
Rather not, we have low signal to noise ratio, and after subtraction we have some looks like peak. And for example, this one, and here it could be located a peak from iron oxide, which is present on the top of the layer.
Okay, so you don't think it's an additional third peak instead of the liquid there?
Yes.
Okay. Good, thanks.
Thank you.
So thank you very much again. I'm very sorry I just missed the question point. So basically, is there any other question from the audience? For the moment, I don't see them. So basically, in 10 minutes, we will continue with the next session. Thank you very much.